That's interesting. Well, good morning. Let's see. I think I put a second sapling homework up for this class. I hope I remembered to publish it. Does that sound familiar or not?
Could you repeat that?
Oh,
Sorry.
I think I put a second sapling homework up. Does that sound familiar or not?
Let me look and I'll get back to you.
Let's see. Oh, what class is that? I keep going to the wrong one. This is. Man, I need to.
Are you talking about the constant acceleration homework?
Yeah, where did I put that? Huh.
I see it.
Okay, is it under assignments?
It's right under the one. It's right under the first homework. If you scroll down.
Okay, I need to go back to my modules here then. Let's see, week 1, day 1. Where did I put it? Huh.
At the very top.
Week 1, day 1, week 1, day 2.
In my thing, it says upcoming assignments and events.
Oh.
And it's the first one.
Okay, I'm not seeing the student view, that's why. Okay, is that on the home page probably, huh? Maybe. Wow, I'm not at all seeing it. I know I put it up here, but I just don't see where it is. I see a to-do thing. Yeah, let's see, I'll have to, I think I've got a sample student I can log in as, and then I can see it better. But when's that due? When did I make it due? Oh, wow. Sorted useful files. I think I did put an announcement about it up. Man, my computer is just frozen this morning. Oof. Oh, significant figures quiz and new sapling homework. All right. I do have an announcement up for it, so I'll clear out of the student view. Okay, well, today is more stuff with Freefall. We're going to start solving more problems having to do with that. And I'll try to, when I do those things, keep referring back to the formula sheet to familiarize ourselves with the freefall equations. Let's see. Where in the world did my picture go? There it is. Okay, so I'll switch over to the IPVO thing again. And freeze the focus. Okay. And this is all constant acceleration stuff. So the equations that we have for free fall constant acceleration, and I'll just go ahead and write them down again, or compare them to the x free falls that we had, or x constant acceleration. Whoops, that was supposed to be part of this. For constant acceleration in the x direction, we had stuff like v naught plus at. We had x equals x naught plus v naught t plus 1/2 at squared. And we had v squared equals v naught squared plus 2a times x minus x naught. So those were things, equations that we dealt with, and I think one way or another we managed to use every one of these equations and things. With free fall, we're going to have that the acceleration is always going to be minus g, and g by itself, I tend to just write out of habit 9.81 meters per second squared. Your textbook most of the time uses 9.80 meters per second squared. It doesn't matter which one you happen to use. It's not going to be far enough off. Sapling actually gives you, I think lets you have a 2% error on your problem, which would actually be a difference out here on the 8, not that digit following it. So don't worry about the difference. But when we do that, we'll get equations, and we'll be in the y direction instead of in the x direction. And the equations I'm going to write down here are all assuming that up is positive. And that's why we put a minus sign on here, because the acceleration is going to be down. So v equals v naught minus gt. Okay, it's just like this. It just happens to have a acceleration that's in the negative direction, and it has a value of little g. So we'll have that. And then we have y equals y naught plus v naught t minus 1/2 gt squared. So the only difference from this one to this one is I changed x to y and x naught to y naught and a to minus g. And so that's all that happens. V squared equals v naught squared plus 2a times, y minus, I was copying that equation down. Forget this. It'll be v naught squared minus 2 times g times y minus y naught. So that's what v squared is going to equal. Okay, now all the problems we're going to do today, I'm going to use these equations to solve them. And then starting, actually tomorrow, I may want to do some chase problems. I'm not sure. And we actually might spend another day on free fall. But then we're going to take on a situation where we will have motion in both the x and the y direction. And so then once we start that, I'll have to do something so that I distinguish between the velocity in the x direction and the velocity in the y direction. So I'll tag another little subscript onto them. But for today, we're okay just with the set that we have here. And these are in this area of your formula sheet. So here's a classic problem. I don't know if you knew it or not, but the Space Needle over in Seattle has a couple of restaurants on it. And used to be, there was only one restaurant on it, and it was way up at the top of it. The top of the Space Needle was actually a 2-story thing, or is. And the top story is just the observation deck. That's the only part I've ever been to. But the one below that is the Space Needle restaurant. And it's, I don't know if it still is or not, but it was designed so that it rotated once per hour. So if you were having dinner there and were seated at the restaurant for an hour, you'd have your view change by 360 degrees while you were eating. It wasn't fast enough to give you motion sickness or anything. Never ate there, but it's not my kind of place, I guess, where you have to pay an extra $30 just for the experience of sitting down in some place. I'd rather have a hot dog on the deck above, I think. But anyway, dishwasher accidentally drops a handful of forks over the edge. a woman on the ground 150 meters below happens to see the dishwasher drop the forks and immediately warns people to get out of the way. How long do the people on the ground have to escape the lethal flying forks, and how fast are they moving when they hit the ground? Well, let's see how we can do this thing. Start off with a sketch here. This is a rough approximation of the Space Needle here. It's got this big disc up here and a point. And so this would be y equals y naught up here. This is where the forks get dropped from. And I'm going to let y equal 0 down on the ground here. And so it's going to be 150 meters from down here to up there. Okay, let's see. Well, let's figure out part A. How long do we have to get out of the way? That's time. And I'll look at my equations here. If it's how long, I don't really care how fast they're going when they hit the ground. That's part B anyway. But I might be able to use this equation here to figure out how long they would take to get down there. I know what y is going to be at the end. It's going to be 0. They hit the ground. Y naught is 150 meters. Ordinarily, this equation here could turn into a quadratic equation, but in this case, it won't. And the reason I know it won't is because, or at least not a bad quadratic equation, is because V naught is 0. It says he drops the forks. Okay, he doesn't throw them downward, he just drops them. And so V naught is 0, which makes this term disappear. And so I'll have a 1/2 GT squared that I can set equal to just a pure number. And that's not hard to solve. So you'll see how hard it is to solve. So I'll use that equation. So y equals y naught plus V naught y, whoops, just V naught so far, minus 1/2 GT squared. Now, my unknown is t, but I know some stuff in here. I know that y is equal to 0 when it hits the ground, so that'll be part of it. I know that V naught is 0, so that makes this whole term disappear, and I know that y naught is equal to 150 meters. So let's see what we get when I plug those into here. I would have 0 equals 150 meters minus 1/2 GT squared. And I know G is 9.81 meters per second squared, so that's a number I know. And if I kick this term across, my equation turns into, it becomes positive, 1/2 GT squared is equal to 150 meters. If I multiply both sides by 2 and then divide by G, that's 2 algebra steps at once, but see if you can do that. I would get 2 times 150 meters divided by G is equal to 300 meters divided by, now I'm going to finally write in the number for G, 9.81 meters per second squared. At our latitude, it's closer to that than it is to 9.80. And when I do this unit-wise, I'll do that off to the side here, I would have meters divided by meters per second squared. When you divide by a fraction, you flip it and multiply, so I'll have meters times seconds squared per meter. The meters divide out and I just get t squared in seconds squared. Well, that makes sense. That's not so bad. So 300 divided by 9.81 is about 90, how many sig figs do I have? Probably only 2. So I would say that it's 92 seconds squared, which makes t equal to, just take the square root of that, or raise it to the 1/2 power. And I get about 9.6 seconds. Whoops, 9.6. Oh, well, that's plenty of time to get out of the way. You're not going to have to move very far, although she's probably, this woman on the ground is probably the only one who sees them coming, although it says she immediately warns people to get out of the way. So that was nice of her to do that. Then it says, how fast are the forks going when they hit the ground? How fast? That's velocity. So B, I want to know, V is equal to V naught plus or minus GT, but V naught is 0, so it's just going to equal minus G, which is minus 9.81 meters per second squared, times my 9.6 seconds, and I'll be down to 2 significant figures when I'm done here, and I get a minus sign. That tells me they're moving downward. Big surprise there, but the minus sign tells us that for sure. So if I multiply that time I just got by 9.8, I get, oops, helps to, oh well, 9.81 times. Okay, I get around 94 meters per second, which is actually more than 180 miles an hour. So those forks are going to be kind of lethal, although air resistance would slow them down a bit. You can't really say that a fork is going to have constant acceleration on the way down, but we pretend that they do anyway. So that would be a scary fork going that fast. Okay, any questions on that one? I guess you have to pretend that's the Space Needle, but okay, let's see what else we can do. Here's one where we're supposed to get a bunch of different position and velocities for something. Position and velocity at times of 0.500, 1.00, 1.50, and 2.00 seconds for a ball thrown straight up with an initial velocity of 15.0 meters per second. Well, I can write down the equations, position and velocity. Position is y. So, and it says take the point of release to be y naught is equal to 0. So this would be like a person standing on the ground or something like that. And in one hand, they've got a ball and they throw it upward so that they've moved their arm upward like this. And when it's released from their thing, we're going to choose that to be where y naught is equal to 0. So we're measuring y from the height that they release the ball at. Okay, well, equations that apply here, y is equal to y naught plus v naught t minus 1/2 gt squared. In this case, we're given the times that we're supposed to figure out, and so I can do stuff like that. If I was smarter on my calculator, oh, I think I do know how to do it on my calculator, but I don't want to get too fancy with that. I'm just going to do brute force. But this equation will become, with an initial velocity of 15.0 meters per second, it will end up being this. Y naught was 0, remember. It will become 15.0 meters per second. That's V naught times T minus 1/2 times 9.81 meters per second squared times T squared. And so this is the equation that describes where it is as a function of time. And I just have to take these times and plug it into this equation, and it'll tell me where it is. It also asks for the velocity at all times, though, and that's the equation that looks like v equals v naught minus gt. Well, let's see, v naught was the 15.0 meters per second minus 9.81 meters per second squared times t. And so those are the equations that I'll just plug all these values into and be a bit repetitious. This would be something nicer to do on a computer, but in fact, I don't know where I put my TI-83. It's around here somewhere. TI-83s, you have the ability to do this, but I'll just show you how I do it for 0.500 seconds. And then I'll just fly through the repetition of this. So 15 times 0.5 minus 0.5, that's what 1/2 is, times 9.81 times 0.5 seconds. But this time I square the 0.5 seconds, and I get at t equals 0.500 seconds, y is going to equal 6 point, how many significant figures do I have? Looks like I have 3 significant figures, so 6.27 meters. V is going to equal, I just take my 15 minus 9.81 times 0.5. No, yeah, it was 0.5 seconds. That's what's going on. Okay, and I get 10.1 meters per second. At 1 second, I would do the same thing. I would get y is equal to, just plug in the numbers, but stick a 1 in for t. So 15 times 1 minus 0.5 times 9.81 times 1 squared. Now really, multiplying by 1 and multiplying by 1 squared doesn't do anything, but I get y is equal to 10.1 meters, and v is going to equal 15 minus 9.81. So 9.81 times 1, but that's just that. And I get v is 5.19 meters. So this is getting kind of repetitious, but maybe it'll get more interesting. C. Let's see. T equals 1.50 seconds. So I'll just do this same thing again. 15 times 1.5 minus 0.5 times 9.81. Whoops, wrong symbol. 9.81 times 1.5 squared. Hope I did this right. Looks like I get about 11.5 meters at that time. And V at that point is going to be 15 minus 9.81 times 1.5. So I just replace the t with 1.5 again, and I get Is that right? 9.81 times 1.5. I get minus 0.29. That doesn't seem right to me. Let me do that, plug that in again. 15 minus 9.81 times 1.5. Okay, makes more sense. Plus sign. I don't know how I got a minus sign on there. It would be 0.285 meters per second. Something to notice. Well, at half a second, it was still going upward at 10.1 meters per second. Half a second after that, at 1 second, it was only going upward at 5.19 meters per second, if I have the units correct. And then half a second after that, it's only going up at 0.285 meters per second. It's actually losing 9.81 meters per second every second that goes on, but every half second that goes on, it's losing 4.9 meters per second. And so I would expect at 2 seconds, it's going to have a negative velocity and won't be going up anymore. It's about to come to a stop. When you throw a ball upward, it accelerates all the way up, but the acceleration is opposite the direction of motion, and so that's slowing it down. So finally, D at t equals 2.00 seconds, y is going to equal 15 meters per second times 2 seconds minus 1/2 times 9.81 meters per second squared times 2 seconds squared. Let's see what that turns into. So 15 times 2 minus 0.5 times 9.81 times 2 squared. Okay, at that time, I get 10.4 meters, which is less than where it was here. So sometime between here and here, it reversed direction. It was going up all this time. Now it's on its way down. And its velocity at that time, 15 minus 9.81 times 2 is equal to minus 4.62 meters per second. So yeah, now it's on its way down. And so from what I've figured out, I don't know exactly when its maximum height was reached, but I can figure that out. And I don't know if we're not asked to do that on this problem. We're just supposed to figure these things out. But I don't know if any of the examples I'm doing have you figure that out. I'll do it. Right here, I'm going to say part E. When does the ball stop going up? Okay, we can actually figure that out if we look at the velocity equation. V is equal to V naught minus GT. The ball stops going up when V is 0. What the ball does at the very top is it's been going upward, so it's had a positive velocity. After that maximum height point, it starts downward. It'll have a negative velocity, but at the time it's at the highest point, the velocity will be 0. And so I just set that equal to 0, and this equation isn't too bad. That means V naught minus GT is 0. that means if I kick the minus GT across, I get V naught equals GT, or T is equal to V naught over G. That's a value for the time when the thing starts coming down. So I just take my initial velocity of 15.0 meters per second and divide by 9.81 meters per second squared. Now let's look at the units to make sure we get something that's reasonable here. I'll just do it on the back of this one. Meters per second divided by meters per second squared. When you divide by a fraction, you invert it and multiply. So that'll become meters per second times seconds squared per meter. Okay, the meters divide out. Seconds squared over seconds is just seconds. Yeah, that'll give me a time in seconds. Then I just plug in the numbers. So let's see what we get. 15 divided by 9.81. Okay, and I get about 1.53 seconds. That's about what I would have guessed, because when I looked at this thing for C, when I calculated the stuff at 1.50 seconds, I got that the upward velocity was only 0.285 meters per second. That's not very fast anymore. It's slowed down a lot, so I would have expected that it was going to stop shortly after this. And sure enough, 0.03 of a second later, it had stopped. So it didn't take too long. But this is something that maybe we can remember doing this to figure out how long it's going to be going up. You can just set that velocity in the y direction equal to 0 and do that. We could also use that to figure out the maximum height. And in fact, let's go ahead and do that. This is part F. What is the maximum height and I'll say above the launch point, which is the person's hand. We don't know how high the person's hand is above the ground, but everything is in relation to the launch point. Well, if I take this formula for the time that it's going up and plug that into the y equation, I might be able to do that. Or, well, that's one way of doing it. I can go y equals y naught, which is 0, I forgot, plus v naught t minus 1/2 gt squared. And I will get, let's see, v naught times v naught over g, whoops, v naught over g, minus 1/2 times g times v naught over g squared, which is going to be v naught squared over g minus, let's see, that's going to be 1/2 times g times v naught squared over g squared, which, oh, this takes algebra skills. Good grief. V naught squared over g minus, well, this g over g squared leaves me a g on the bottom. It's actually minus v naught squared over 2g. And if I multiply top and bottom of this one by 2, I can get a 2g on the bottom. And then I've got on top, I'll have 2 v naught squared minus v naught squared on top, which is just 1 v naught squared divided by 2g. And you can work through the algebra of that to convince yourself that I was right. But I would get v naught squared over 2g. And so I just plug in the numbers. I'd have v naught was 15.0 meters per second. which I square, and divide that by 2 times 9.81 meters per second squared. Unit-wise, on top, I'm going to have meters squared per second squared. On the bottom, I'll have meters per second squared. Invert and multiply. You've seen me do this a few times. Meters squared per second squared times second squared over meter. The second squared divide out. Meters squared over meters is just meters, and that's good. That'll tell me how high it goes. So whatever it happens to be, y is equal to 15 squared is, turn on your calculator first, clear, 15 squared divided by, have to wrap that bottom in parentheses to put it in my calculator, 2 times 9.81, then I get about 11.5 meters. Hey, that's about what I would have guessed. So let me show you another way to do that last problem, how high it goes. If that's all you care about, there's that other equation that we didn't use yet. V squared is V naught squared minus 2G times Y minus Y naught. Okay, now remember, when it gets to the maximum height, V is going to be 0. And we said that Y naught was equal to 0 as well. So this equation turns into 0 equals V naught squared minus 2 times G. If Y naught is 0, this part just becomes 2GY. Kick the 2GY across. 2GY equals V naught squared. Divide by 2G and you get Y is equal to V naught squared over 2G. Oh, that's what I solved for. But this was a lot easier to do than to actually figure out the time it spent on the way up and then plugging that time into here and doing the algebra. So a little bit simpler way to do it, but you would get the same answer. Okay, recycle that. Lots of practice with this thing. Okay, a rock, oh, this is one out of your book. A rock is dropped from a height of 75 meters above the ground. Determine the distance traveled in the first second. Huh, okay, a rock is dropped from 75 meters up. I'm going to let y equal 0 on the ground, just for the heck of it. And up here at 75 meters, that's where y naught is. Now, other bits of key information, it is dropped. So that tells me that v naught is 0. Okay, it's not thrown down, it's just let go of. So I have that. So, well, y is going to equal y naught plus v naught yt minus 1/2 gt squared, but v naught is 0, so that makes the middle term go away, so it's just going to be y naught minus 1/2 gt squared. The distance traveled in that first second. Well, this will tell me where it is after that first second, and yeah, actually, the distance traveled in the first second, trying to think, do I want to express it this way? I think I could. after 1 second, it's going to be at some new, I'll call it y of 1 here. I can think of that as y of 1 second. Y of 1 is going to equal y naught minus 1/2 gt squared. A little bit of algebra swapping here. If I kick the 1/2 gt squared across and subtract the y of 1 from each side, I'll get 1/2 gt squared equals y naught minus the y of 1. This represents the distance it traveled. Okay, it's going to be positive. Otherwise, I could just figure out what y of 1 second is, which would be the 75 meters minus that thing, and then calculate the distance between that point and this one. But this is a way of doing it all at once. And anyway, 1/2 gt squared is going to equal 1/2 squared of 9.81 meters per second squared times 1 second. They just say in the first second. They don't say how many significant figures. We could put as many as we want, and we square that. And what you end up with, since 1 squared is 1, is half of 9.81, which is about 4.91 meters. On Earth, anytime you drop something, in the first 1 second of falling, it will travel 4.91 meters. And doesn't matter how high above the ground is, in the first second, it's going to fall 4.91 meters. So we can get that. Another way that you could get that, and this is almost easier, you could start off with y naught equaling 0 here. Y at the end is the 75 meters, and you can say downward is positive. We haven't done that, but if down is positive, and sometimes this is useful, especially if all of your motion is downward, and so you're standing on a bridge and you drop a rock, then you can rewrite these equations. Y equals y naught plus v naught t plus 1/2 gt squared. And that's how the equation looks if downward is positive. We had a minus 1/2 gt squared when up was positive, but we can decide down is the positive direction. Then you'd also get v is equal to v naught plus gt. Now in this problem, we've got v naught equal to 0. And so this is 0, this is 0. So v equals gt and y is y naught plus 1/2 gt squared. So that's a way that you could do this problem if you wanted to. And it might make sense. Determine the final velocity at which the rock hits the ground. And in preparation for the next part, how long it takes to hit the ground. Well, when it hits the ground, we can stick with the down is negative. Stick with this equation if we want to. We can say, yeah, we'll figure out how long it takes to hit the ground first, and then take that time and plug it into the velocity equation. So here's what happens. When it hits the ground, y is going to equal 0. So y equals 0 is going to equal y naught minus 1/2 gt squared. And so this will be a two-stepper, but it's not so bad. I just bring that to the other side of the equation and get y naught equals 1/2 gt squared. Multiply both sides by 2. 2y naught equals gt squared. Hopefully you're getting good at imagining what to do next on these algebra things. T squared is going to equal 2y0 divided by g, which is 2 times 75.0 meters divided by 9.81 meters per second squared. Meters over meters per second squared, that's going to give me units of seconds squared. I've already done that once today. And I get, let's see, about 15.3 seconds squared. That, so the time it takes to hit the ground is going to be whatever the square root of that is, a little less than 4. 3.91 seconds. And then it says the velocity at which it hits the ground. Well, that's going to be v equals v0 minus gt, but it was dropped, so v0 is 0. So it's just going to be minus 9.81 meters per second squared times 3.91 seconds. So times, and it looks like about 38.4 meters per second. And whoops, with a minus sign, because it's headed down. Okay, now, how about the distance traveled in that final second before the rock hits the ground? How could I figure that out? Well, I know the time that it takes to hit the ground. If I subtract 1 second from that and figure out the y position at 2.91 seconds, that'll tell me how far it is above the ground 1 second before it hits the ground. And so that height will be how far it travels in the last second. So let's figure that out. So y at 2.91 seconds is going to equal y0 minus 1/2 gt squared. Remember, the v0 is 0. It was dropped. So 75.0 meters minus 1/2 times 9.81 meters per second squared times 2.91 seconds, and I square that. So the y 1 second before it hits the ground is going to be 75 minus 0.5 times 9.81 times 2.91. I think I got that right. And I get, I think, 33.5 meters. So that's how high it is 1 second before it hits the ground. And in that next second, it travels those 33.5 meters and smacks into the ground. So, oof, these are getting more complicated, it seems like. But using constant acceleration equations, looking at what I know and what I need to figure out. So that's something that just, you get better at it with practice. And if you don't practice, you won't get better at it. So let's see. I don't know that we have time to do this one. Let's see, maybe we can. We might be able to set this up. Someday in the future, a Lunar Lander is making its descent to Moon Base 1. And I just read this weekend that SpaceX has been given the contract by NASA to develop the next moon lander. So that'll be kind of neat. We're going to return to the moon after, let's see, 50 years away from it. Actually, next year it's going to be 50 years since the last moon mission. So the lander descends slowly under the retro thrust of its descent engine. And what that is if this is the surface of the moon here, and the moon lander had these, I don't know, legs on it, I guess. We'll just sort of make it look like that. Anyway, it's down there, and it had a rocket engine that it fired as it was descending toward the moon. So it was shooting, you know, propellant out of the bottom of it to slow it down as it descended toward the moon. I don't know if you've ever watched any of the landings of the SpaceX rocket boosters, but they're the first people who've ever done this. And it took them a bunch of tries before they had one that worked. But when SpaceX launches stuff into space, the first stage of the rocket, which NASA and Russia and China and everybody who'd ever launched stuff just threw away that first booster, but SpaceX figured out a way to get it to land. And they've actually been landing them on barges in the Atlantic Ocean, and they've done it during stormy conditions even, and gotten them to land and stay upright. Now, they didn't stay upright right at first, and I remember one fall quarter showing my class one of their attempts where the thing landed on the barge and then blew up, but now they're getting it to work. And the thing is descending toward the barge that it lands on, firing its rocket engine, and then just a brief instant before it hits or lands on the barge, it stops firing the rocket engine. So that's what's going on here. Anyway, it descends. The engine is cut off when the lander is 5 meters above the surface and has a downward speed of 0.805 meters per second. This is going to be V naught for our situation, but it's downward. And so V naught is going to be minus 0.805 meters per second. Y naught is going to be 5.00 meters. And let's write the y equation. Okay, y is going to equal y naught plus v naught y t minus 1/2 gt squared. Okay, y naught is 5 meters. When it reaches the surface, y will be 0. So one way to solve this problem would be to set this equal to 0, this equal to 5 meters, this equal to minus 0.805 meters per second, and this is going to be not 9.81 meters per second, but 1.61 meters per second squared, because the acceleration due to gravity is different on the moon, because the moon has less mass and a smaller radius, combining to give it that value. Another way to do this, though, is to say this. V squared is going to equal V naught squared minus 2g times y minus y naught. Okay, and we know V naught, it's minus 0.805 meters per second. You're going to square it here and get a positive value. This equation has a minus sign in it, but y is going to be 0, and so you're going to have minus y naught multiplying that thing. And I'll just set up the equations and you can solve it if you want to, but it would be minus 0.805 meters per second, but you're squaring that, plus 2 times g, or you can think of it as minus if you want, but the g is going to be 1.61 meters per second squared, and then y naught is going to be 5.00 meters. And work through this and convince yourself that I've got the right equation here. when this gets squared, it's going to be positive. But convince yourself that when I went from here to here, that I didn't make a mistake. Okay, that's how you'd solve that problem, and that's as far as we can go here today. This afternoon, I'm going out to school, and I'm going to do the data gathering for the lab that I'm going to have you do this week, and I'm going to try some different things in it. But the lab is just called, I think, speed and acceleration or something to that effect. And usually I have you go through some measurements for it, but I'm going to do them today, and I'm going to try something new where some of the measurements I'm going to actually use a computer with a photo cell to measure, or a motion detector to measure some things. And we'll see how that happens to work out. But I'll be doing that and then providing you with that lab data. And I'll take pictures while I'm doing it. Take my camera with me and record some video and stuff. So anyway, any questions? I'll stop the screen sharing here. Lots of problems today that we solved, and it's getting kind of mathy. It is. That's the nature of the thing. But I'll keep going with this. Let's see, free fall today. We may do a little more free fall tomorrow. And then I want to start considering two-dimensional motion, where in addition to up-down motion, there will also be some sideways motion. And that's called projectile motion, where you launch a projectile. Technically speaking, if you throw something straight up, it's a projectile too. But we'll see how that goes. Okay, any questions for today?
So the assignments that are out right now is the SIG-FIG quiz and the sapling thing, and that's about it, right?
Right, yep,
Boy.
that's it. And then soon I'll give you the data for this week's lab. So,
Do you know when our first test is going to be?
let's see, probably around the end of next week. I usually have the tests after 4 weeks, 8 weeks, and then for the last 2 weeks, that material we don't have a separate unit test on, but it'll be on the final. So we have 2 unit tests and then a comprehensive final test in this class. So yeah, around the end of the fourth week, beginning of the 5th week, something like that. Okay. All righty. Well, have a good day, and I'll see you tomorrow.